I start?
Yes, Miss.
Okay,
Yes,
great.
Miss.
Wonderful. Right. So this morning's topic is pretty much a continuation of what we've begun, and that is mainly the SN2 reaction mechanism. Now, you guys have been informed already that the reading material for this topic is coming from chapter 8, Soderbergh volume. Sorry, I think I have volume 2 here, but I think chapter 8 is the last chapter in volume 1. So just verify that. Yes, it's the last volume. It's the last chapter in volume 1. So just note that correction there. But the page numbers are correct. All right, so today's topics that we're going to be covering, and hopefully we're able to get through all of it, let's see, is the SN2 reaction mechanism. We're going to touch a bit on SN2 nucleophiles and perhaps SN2 electrophiles, and then finally biological SN2 reactions. This is a course that is relevant to persons that are in the biological sciences, and so there is a special tweaking that has been done to accommodate those topics that you will be encountering in your areas and fields of study. Now, the general idea is not to deny the synthetic aspects of the chemistry that you will that we are actually interacting with at this time, but to shift focus or to give primary focus to the biological context. All right, so I am going to turn my video off, and we will take this journey together for the next, let's say, 40 or so minutes. All right, so as we were saying, there are a number of trends that we had discussed previously, and those trends are pertaining to the reaction, the substitution reaction, which in this case is SN2. Now, the trends will change depending on, some of these trends will change depending on the context of the reaction. So if we are talking about an SN2 reaction, we will find that there will be particular patterns that govern that reaction that will allow us to identify appropriate electrophiles and nucleophiles for the reaction itself. And then when we begin to have our conversation about the SN1 electrophile, sorry, not electrophile, but reaction, then what will happen is we will actually be able to see how to identify the appropriate players with regards to those specific reaction contexts. So in other words, SN1 electrophiles and SN2 electrophiles may come from the same pool, but the parameters that guide the electrophilicity for those reactions will be varied. And so I just want to prepare you all for that in advance, so that when we encounter it, you will know that we were to see this coming. Similar thing will be expected for nucleophiles and reaction solvents, etc. So the summary here that is before you is the summary of our electrophilicity trends. We would have spoken about this previously, but we did not summarize it. And even this summary is not airtight, in that it is still going to be developed over time. So, but the general tenets that govern electrophilicity are the following. One, electrophilicity is influenced by sterics and electronics. Sterics, when we spoke about it previously, actually speak to the bulk and the size of the molecule itself. So the larger the molecule is, the more it will impact, either positively or negatively, the electrophilicity of the molecule itself. In other words, larger molecules will perform a certain way, smaller, less substituted molecules will perform a different way. As we proceed through the various reaction contexts, we will see how this begins to unfold. Secondly, electronics plays a significant role in determining the electrophilicity of a molecule. So, an electrophile, as you know, is highly dependent on the presence of a polarized bond. There needs to be a charged dipole that is present between your electrophilic atom and your leaving group. The larger the charged dipole, the longer the bond length, and the better the electrophile is. And as you know, we would have had that conversation as well about those variables that play out in this context or in this particular scenario. Suffice it to say that electronics basically are part of what governs the reactivity of any chemical compound. So what you will find going forward is that reactions will always be presenting a display of steric parameters and electronic parameters. There will always be sort of there will always be kind of just interplaying with each other at various stages, and different combinations will actually determine whether or not the reaction goes forward, whether it's favorable, and if it does go forward, whether it does so fast, slow, or intermediate. All right, so having said that, less substituted electrophiles are better electrophiles generally for SN2 reactions. Electrophiles that are bonded to good leaving groups are good electrophiles in general, because, as we just said, good leaving groups need to do exactly what leaving groups should do, which is leave. And the better they are able to do that, or the better they are at that, the better the electrophile on a whole will be. More effective it will be at facilitating the substitution reaction. Bulky leaving groups increase bond length and thus electrophilicity. So, as we had also said, the larger the leaving group, the longer the bond length. The longer the bond length, the weaker the bond. The weaker the bond, the easier it is to break. The easier it is to break, the better the electrophile. All right? So, moving on.
Excuse me, Miss.
Yes.
Can you go over the last point, number 4?
Okay, sure, no problem. Maybe I can just annotate quickly, and then that way you guys can see it as we go. Yeah, that's a bit of a mouthful. So what we were saying is, let's see, we're saying that bulky leaving groups increase bond length and thus electrophilicity. So increased bond length leads to decreased bond strength. So in other words, increased bond length leads to weaker bond. And the weaker the bond, the easier it is to break. So I should say that leads to ease in breaking. And the easier the bond is to break, let's see if we could climb up here. The easier the bond is to break, the better the electrophile. Is that clear?
Yes, Miss, much better.
Thank you. I didn't say it exactly like I said it before, but the general idea is there's a correlation between bond length, bond strength, and electrophilicity. What you need to know is that there's an inverse relationship between bond length and bond strength. The longer the bond, the weaker the bond. The shorter the bond, the stronger the bond. Strong bonds lead to poor electrophiles, basically. Right? All right, so thank you for that question. Let's clear that. Good. So moving on, that puts us in a stead where we can now look at our leaving groups. So our leaving group trends are: leaving group ability is influenced by sterics and electronics, similar to our electrophilicity trends. Bulky, larger leaving groups are better leaving groups. Now this is almost kind of like a reverse or an inverse relationship. We saw for the electrophiles, the smaller they are, the less bulky they are, the better they are at being electrophiles. In the case of leaving groups, we're finding that the larger the leaving group is, the better it will be as a leaving group. Leaving groups are generally poor bases, and if we are wondering what poor bases look like, we don't need to look too far. We can see that weak conjugate bases of strong acids are good leaving groups. So you don't have to memorize a whole list of compounds because you actually know them already, and you just now can draw from that pool of compounds that you are already familiar with, except that now you're adding a new layer of characteristics to that pool, basically. All right, the fifth item basically is saying to us that bulky leaving groups increase bond length, and the same correlation that we identified a few moments ago holds true, which is that once you increase your bond length, you will increase your electrophilicity, because longer bonds equate to weaker bonds, and that means that the leaving group is able to better leave or leave faster. All right. So there are some things for us to note about nucleophilicity in the SN2 context. And while we did speak a lot about nucleophiles in general, we have to now go back and do some tidying up and fill in some spaces. So you would have been familiar with this this slide, where we have for you the horizontal trends of the periodic elements, and we are seeing that essentially nucleophiles, we know that they are good bases. We also know that nucleophilicity typically runs parallel to basicity. However, we were introduced to some exceptions. And the exception that is important to be aware of is the antiparallel exception, where we see that nucleophilicity does not run parallel with basicity. The context in which that is present is when we are making a comparison between elements in a group. We identified previously that the reason for this is that there are some situations where, even though An element may be a stronger base, as in the case here with fluoride and iodide. We know that fluoride is the conjugate base of hydrofluoric acid, and hydrofluoric acid is a weaker acid than hydroiodic acid. Hydroiodic acid is a strong acid of the two, right? So we know that fluoride would actually be a stronger conjugate base than iodide would be. So our expectation would be then that fluoride would be a better nucleophile. However, in the context that is before us, we are seeing that that is not the case. And so the correlation is antiparallel. This antiparallel correlation is resulting from the presence of non-bonding interactions with the solvent. So let's just give a little bit more attention to that so that we can see what's going on. We already did speak, yes, about how the solvent cage encircles the nucleophile itself, and fluoride ions are harder to break free from that solvent cage. You can refer to the slides that I would have posted on the course page just to refresh your memory on that, as well as the recording. But to delve in a little bit deeper, one of the things that we are saying here is, what are those solvents where these non-bonding interactions can be so prevalent? In other words, the point is that the antiparallel relationship does not happen in every situation. It is an exceptional situation, or it's an exceptional correlation that occurs in a specific solvent. And the solvent that it occurs in is a polar protic solvent. So what is a polar protic solvent? A polar protic solvent is a solvent that is both polar and protic. What does that mean? Well, we understand what polarity is. We can generally identify polar solvents. Now we're in a better position to do that. If you have a good handle on electronegativity, you are able to see that dipoles exist in molecules and in molecular bonds, because you know that there is a difference in electronegativity between elements. So that already helps us to identify the presence of polarization within a molecular context. Now here we have solvents that are polar and protic. The protic parameter, or the protic characteristic, is what shows up in the form of a solvent that contains a hydrogen bonding hydrogen atom. So in other words, the solvent molecule must have a hydrogen that can participate in hydrogen bonding. It's important for you to know that, because obviously there are a whole host of compounds that contain hydrogen, but not all of those hydrogen atoms would participate in hydrogen bonding. So when you are looking to identify what your polar protic solvent looks like, you need to be able to see the presence of both of these characteristics. There must be polarity, and there must be a hydrogen bonding hydrogen atom. Now that's a lot of hydrogens to say, but it's important for you to be able to identify and distinguish them. The reason why I'm zooming in on this particular class of exceptions is because in biological contexts, the reaction solvents are polar protic. Your reaction medium is a solvent that is pretty much polar and protic. Living systems are actually comprised of chemical reactions occurring in aquatic solvents, right? So your solvent is water. Water is the general solvent that mostly all living systems do their chemical reactions in. And what that then means is that the reality of how a nucleophilic reaction would occur in that context would have to be based on the trends that I highlighted here. So If something is reversed because of the context in terms of solvent, we need to know it here in this particular class. In a typical chemistry class, organic chemistry class that's for chemists, we would basically just class this as one of the patterns, but not necessarily give it as much focus. Okay, so then to give more attention to what these solvents look like, we already said they include water and alcohol. So essentially, I said the water already, but your other protic solvents, your other polar protic solvents would be your ROH solvents. Any alcohol solvent would be a polar protic solvent. If there is another solvent that contains a hydrogen bonding hydrogen, and it is also polar, that would come under this category as well. And I'm sure that there are those that have already been synthesized and exist, and if we come across them in the course of our journey here in this class, we will be sure to highlight them. But just note that this particular category of solvents are heavily inclusive of water and alcohol solvents. The parallel correlation is observed in all the other solvents where hydrogen bonding is not possible. So as we proceed further, you will see that there are other classes of solvents, and when you encounter those, you will know that those solvents behave in a way as we should expect them to behave where nucleophilicity is concerned. There are no solvent cages formed with those solvents. All right, so going back now to what we wanted to really get into, which is our mechanism. You would have seen this slide before. The SNX notation is important. All right. Now revisiting our schematic at the top here, our curved arrow moves our electrons from being centralized around the nucleophile. By way of this arrow, we are forming a chemical bond between the nucleophile and the electrophile. Our arrow originates where the electrons are because that's the source, and it actually ends or terminates at the electrophilic atom, which is B. In this case, the bond will then form between the atom of this nucleophile here, which possibly is A in this case. This is a general case, but it certainly will be formed between A and B. And that's where you must be sure to be very attentive when you are drawing your reaction mechanisms, because it is not a general bond formation. Bonds don't form between molecules. Bonds form between atoms in molecules. And so it's important for you to know exactly where the bond formation is happening and where the bond cleavage is happening as well. So it doesn't matter how large or complex the molecule is, because at the end of the day, if the reaction is only happening at a specific location in that molecule itself, that's where your focus will be. All right, so the corresponding bond formation is also accompanied by a bond breaking that is occurring between the two elements here. And we know our receiving atom receives the electrons in the bond and basically leaves. This is our leaving group, as we already have discussed. Product AB forms, and our leaving group gains our electrons. All right, so our SN2 mechanism is a concerted one-step reaction, meaning everything is happening at once, meaning that the fastest step is also the slowest step, and therefore it is the rate determining step. So when we are looking at the reaction to tell us more about the speed, the rate, and all of those things, we have to give our attention to that one step. Okay, there's nothing else to look at, so we have to focus our attention there. The absence of a formal intermediate species means that we don't have any intermediate complexes to pay attention to, and it means that we have to give our attention to our transition states based on that intermediate, based on that non-formal intermediate species. So here we have a picture of our transition state in generic form, and here it is what we refer to as bimolecular. The reason why it's called bimolecular is because what is happening is the nucleophile and the electrophile are a part of this transition state. So essentially, we took this molecule and we took this molecule and we combined them to form our transitionary intermediate, where the bonds are not fully formed nor fully broken. And that is actually how we actually find ourselves on our way to the final product. So as is the case, we know that about transition states already, so I'm not going to get into that. But when we look at a real life example, here is our nucleophile, in this case the hydroxide. Here is our electrophile, in this case iodomethane, and here is our product. Now, notice the substitution that is occurring, and notice the leaving group. SN2 reactions occur by way of a stereospecific mechanism, meaning that wherever there is chirality, that chirality will be affected. That's what we mean when we say stereospecific. So it means then that in the mechanism of this reaction, there is an attack by the nucleophile that is coming from the opposite side when positioning the leaving group. So in other words, wherever the leaving group is, the nucleophile is going to come from the other side. That is referred to as a backside attack. Now, as we proceed, we have to then give attention to the fact that this has implications for stereochemistry. Because if this were a chiral molecule, let's say it was an R molecule here, once the attack would have occurred, then the resulting product would have the opposite configuration. As it is currently, what you see before you is the transition state that is being depicted, and it is the bimolecular transition state that I referred to before. So here we have our nucleophile, the hydroxide. It doesn't have a full charge at this point because it is in the process of bond formation. And here we have our leaving group, which is also not fully charged because it is in the process of bond cleavage. So at this point, even though our nucleophile entered into the reaction with a full-blown negative charge, in the transition state species, what you have is a partial dipole for both the nucleophile and the leaving group. The electrophilic center has a partial positive charge. Another thing to say about our transition state is that note the positioning, the geometry of our transition state is such that our groups that are not participating in the reaction itself, meaning all of these hydrogen substituents, are pretty much positioned in a way whereby they're as far away from the action as possible. So all of them exist in a plane that is perpendicular to where the axis of bond formation and bond breakage is occurring. The nucleophile does not approach the electrophile from the front side because it is going to be blocked by the leaving group if it attempted to do so. So if the OH came in this direction, you can see the iodide is already there. This is a hindered approach. Hence, it does not occur and hence the need for the other direction being taken. So here is our VSEPR showing up again, and this time it's showing up in the form of the kind of geometry that our transition state is taking on. As you can see, if you remember anything about how phosphorus bonds, you will recall that phosphorus tends to bond with 5 things. And when it bonds with 5 things, or when it has a coordination number of 5, it exhibits what we refer to as a trigonal bipyramidal geometry. Well, as you would also remember in the previous section of this course, when we were looking at hybridization, one of the things I would have mentioned to you all is that geometry is not specific to an element. The geometry is determined by the orbitals that are participating in hybridization. And so it is dependent on orbitals and not as much on the element itself. So we can say carbon exhibits sp3 hybridized bonding, but carbon is not the only element that does that. So does nitrogen, so does oxygen, so does chlorine, okay? And so in a similar way, when we look at phosphorus and other elements, phosphorus, sulfur, chlorine, I think. I said chlorine is sp3 hybridized, but I meant to say fluorine. But all the period 3 elements that are capable of bonding with larger coordination numbers, they will exhibit a different type of hybridization because they have a greater capacity to accommodate more bonds. So in this case, this geometry is similar to the geometry that phosphorus would display in its hybridization pattern. And it is the geometry that we are familiar with, which is, as is stated here, a trigonal bipyramidal geometry. This is your trigonal part, where you have your 3 substituents in one plane. They're in the same plane and they are 120 degrees apart. And then you have, so these would be referred to as equatorial substituents. And then you have these 2 perpendicular substituents, as in the hydroxy and the iodide. They occupy what we call axial positions. And their positioning or their orientation is in a completely different plane when compared to this one. All right, so in other words, these guys are 120 degrees apart. So here, 120, similar to the sp2 bonds. And then on the plane itself, where you have the corresponding axial bond, what you have is a 90-degree scenario. So this can be drawn more carefully, where you have substituent OH and I, and then you have your hydrogen. All right. So of course your 120 is occurring there between them. Right. So that's your trigonal bipyramidal geometry, ladies and gentlemen. Now that's, again, VSEPR teaches us that the geometry that is resulting is the geometry that gives us maximal distance apart where it pertains to sterics as well as electronics, because we know that these bonds contain electrons, and electrons will repel each other. So they are actually trying to get as far away from each other spatially and angularly. Right, so where does the inversion come from? Once the leaving group leaves, so our hydroxy attacks here, and remember this bond is forming. It's in the process of being formed, and this one is in the process of being broken. Once it actually does break, then what we find is that the hydroxide now becomes fully submerged into the molecular framework, and the iodide leaves. This new substituent puts our hydroxy on the opposite side, and that's what causes an inversion of stereochemistry. Now, as we proceed further, you guys will get to see how this bears true as it pertains to real-life chiral molecules. So if the starting molecule is chiral, the product will definitely be of opposite configuration. And if the molecule is achiral to begin with, the inversion will be inconsequential. There won't be any resulting inversion or anything like that because it's not chiral. So here, again, looking at our starting product, we have our electrophile with the iodine leaving group on one side and the hydroxide nucleophile in the substituted product on the other side. So you should be able to, let's say you didn't have the mechanism before you. Once you look at the reaction itself, one of the first things you want to do is identify the players. First of all, look for your nucleophile. Second of all, look for your electrophile. Once you identify your electrophile, look for the leaving group. If the product is given, look to see, you'll be able to tell what your leaving group is because you'll be able to see what has been removed and what is being replaced, what it has been replaced with. So in other words, it's important for you to pretty much take an assessment of what you're seeing and help to understand, okay, what are the changes that have occurred in this process before getting into the mechanism itself. So once again, to summarize, the SN2 reaction is a one-step concerted reaction that leads to an inversion of stereochemistry. And as we proceed next class, what we will do is we will begin to explore examples of that, as well as getting into electrophiles, more about electrophiles, and more about nucleophiles.